Okay, so last time we start talking about the latent heat for water, for all substances, for phase transition. If it's something called a second order phase transition, you'll have a latent heat. So for water, the latent heat of fusion, this is in SI units, in joules per kilogram. That's 33.5 times 10 to the power 4 joules per kg. Okay, so here's a easier number to remember. It's 80 calories per gram. Okay. What does that number mean? Yep.
Every 80 calories, produces 1 gram, I guess, or?
To melt 1 gram of ice to water, you need 80 calories of heat. Okay. And on the other hand, if you want to freeze 1 gram of water, you have to remove that much heat. Okay. And 1 gram of water is about, can you hold up your bottle? Yeah, so about a cap full of water there. Okay, that's about 1 gram of water. So to melt that much ice, you need 80 calories of heat. Okay, and the latent heat of vaporization for water is about that much water. If you want to convert that to steam, if you want to vaporize it, you want 540 calories of heat. Okay? And conversely, if 1 gram of steam condenses to water, it will release that much heat. Okay, so for instance, you might have heard of the following. Okay. At least all firefighters know about this. Okay. What would you rather have happen? I throw 1 gram of 100 degrees Celsius water at you, or I throw 1 gram of 100 degrees Celsius steam at you. Throwing steam is harder, but anyway, let's not worry about that. They're both at 100 degrees Celsius. Would they cause the same burn? They're at the same temperature. Okay, why? Why not?
I don't know the why, but I believe the answer is the water. We'd rather the water.
Yeah, so that's correct. So you would rather have water thrown. Okay, we just learned that steam has, at the same temperature, has 540 calories of heat more. Okay, so when you throw steam at you, when that steam condenses to water, it has released 540 calories of heat, which burnt you. And now this has become water at 100 degrees Celsius. It'll burn the same amount as that. So steam burns are bad. You don't want that. Okay. Of course, we saw an example of using this number. So to vaporize 1 gram of water, your sweat is essentially water, you need 540 calories of heat. Okay, so we take advantage of that in our cooling system. Okay, you saw it last time that the way you cool. Okay, so just sitting, while you guys are sitting, you're generating 100 joules of heat per second. Okay, and you have to get rid of that heat so your temperature doesn't rise. And if you went for a run, you would generate about 10 to 15 times more heat. Okay, and your cooling system has to work to maintain a constant temperature. Okay, so our cooling system mainly consists of producing sweat, and when 1 gram of sweat evaporates, it takes away 540 calories of heat. Okay, that's your cooling mechanism. So when sweat evaporates, it removes heat from our bodies. All right, so if your sweat will not evaporate, then you won't be able to cool your body. So when does this happen? When does your sweat not evaporate? What's that? No, you can wear all the clothes you want in Alaska, and your sweat will evaporate. 100% humidity, Florida. Okay, so when there's 100% humidity, then sweat will not evaporate. What does 100% humidity mean? Okay, so at every temperature, okay, and let me do a simpler example. Let's say we have a glass of water. So for instance, there's a glass of water, soda, or you can open your water bottle. What do you think will happen if you have a glass of water? Okay, so what happens is the fastest molecules in the water, they'll escape. Okay? And there's water vapor in the atmosphere. Those water molecules are also coming in. Okay? If if the humidity is less than 100%, then more water molecules will escape than come in. Okay? So for instance, in this room, the humidity is 50% relatively. Okay, so that's one of the things that air conditioning does. Okay? It maintains low humidity so your sweat can evaporate and you're comfortable. Okay, that's a cheap way to make you comfortable. Okay, so you've got to make sure your sweat evaporates. Okay, for every temperature, there's a maximum amount of water vapor that the atmosphere can hold. So this table shows you that. Okay. So for instance, in this room, the temperature is about 20 degrees Celsius. Okay, so 20 degrees Celsius. And this is saturated vapor pressure, which is 17.5 millimeters of mercury. Do you guys know what is atmospheric pressure? 760 millimeters of mercury. Okay, so saturated vapor pressure, that's the partial water vapor pressure, that's 2% of the atmosphere. Okay, so that 760 millimeters of mercury is being provided by 2.5% is provided by water vapor, and the other 97.5% is provided by nitrogen and oxygen. Okay. And this tells you the saturated vapor density. At this temperature, the maximum amount of water that the atmosphere can hold is 17 grams per meter cube. Here's a meter cube. This much water, this much atmosphere, if it's 100% humidity, the amount of water would be 17 grams. That's about a half mouthful. Yeah? So if there is 8 grams of water vapor, what does that mean? 50% humidity. Okay? And so that's what that's maintained. All right, so again, for you to cool, if there's maximum water vapor in the atmosphere, your sweat won't evaporate. Okay, and you can't cool down. All right. All right, so here's an absolutely amazing fact. So apparently, so if this is a large oven, and here's a piece of steak, and that's you in the oven. So that's the temperature is 260 degrees Celsius. So your cooling system is so good that you can stay there long enough for the steak to cook. And then you can walk out. See, the steak doesn't have a cooling system. It's dead. Right. and your cooling system is good enough where you could walk out. I don't know if you'll be hungry to eat the steak, but you can walk out. All right, so again, what we'll do is we'll talk about a couple of numbers. What is the latent heat of fusion for water? But 80 calories per? Yep, very good. And actually, we'll do a lab to measure this. So it takes 80 calories of heat to melt a gram of ice. I'll show you a couple of examples where nature moves enormous amounts of energy. Okay. So if you want to freeze 1 gram of water, you have to remove 80 calories of heat. Okay. So here's Lake Superior, one of the smaller lakes. So it's half the size of Florida. Okay. So imagine this. Here is Florida. That's Lake Superior. During the winter, as much as 150 centimeter thick layer of ice forms on the lake surface. So that's my height. So imagine covering Florida with a layer of ice that thick. What do you have to do to make that much ice? You have to remove a lot of heat. You guys remember how to freeze a lake? How do you remove all that heat? You just flip a switch and make the air cold. Heat will flow out on its own. The question is, how much heat do you need to remove? Look at this. 10 million atom bombs. The heat contained in 10 million atom bombs. That's how much heat you have to remove. And that's just one lake. And then what do you do 3 months later? I'm sorry?
Put all that heat back.
Melt all the ice. I mean, the amount of energy nature moves is enormous. Okay? Of course, so this cold air coming down from Canada absorbs all this heat and warms up. So these guys are happy. Yeah. All right, now we'll talk about heat transfer. Okay, so which way does heat flow? From higher to lower temperature. Okay? And there's 3 mechanisms for heat transfer: conduction, convection, and radiation. Okay, so this diagram shows you all 3 ways of heat transfer. Okay, so you can take a piece of metal and heat will be transferred from this flame to you via conduction. Okay? This is radiative heat transfer. Okay, you're getting heat via electromagnetic radiation. Okay? And this is convective heat transfer. How is this heat transfer happening? Huh?
It's transferred through a medium.
Yeah, how? How?
Air.
Okay, how?
The fire heats there in the air.
Mm-hmm.
Touches you
Why does it touch you?
because it rises.
Very good. Okay, so what happens is this flame warms the air, air expands, it becomes less dense than the surrounding cold air, and it rises. It's like if you immerse a piece of wood in water. If something is less dense than the surrounding fluid, it'll rise. Okay, that's an example of, this shows you, that's why flames on earth are like that. Okay, so when you light a candle, it warms the air, and the rising air shapes the flame like that. Okay? So you have a buoyancy when there's a, okay, this will happen when in a gravitational field. This is a candle lit in the space station. It's a microgravity situation, and hot air is not rising there. And so you see the flame is spherical. Okay. Anyway, so there are 3 methods of heat transfer: conduction, convection, okay, when heat is carried by a moving fluid. Okay, so you have convective heat transfer only in fluids, okay, and radiative heat transfer. And we'll look at each method of heat transfer. Okay. This is important for many purposes. Anyway, okay. So here's a solid. In a solid, atoms are in fixed location, and if this end is hotter, that means these guys are vibrating with greater amplitude. Their average kinetic energy is higher than the kinetic energy of these guys. Okay? And what happens is this guy will bump into his neighbor, transfer some of his energy. This guy will bump into his neighbor, transfer some of his energy, and so on, all the way to the end. Okay? And this goes on till when?
Never stops.
I'm sorry?
Transfer
Until
never
the
stops.
net, the net heat transfer.
Say that again.
Until the net heat.
Transfer is zero. Okay, this keeps on happening till the temperature is uniform everywhere. Okay, so the amount of heat going here is equal to the amount coming here. Okay, so heat transfer happens as long as there is a temperature difference that is maintained. Okay, the important thing here is that the molecules themselves are not moving. Okay, they're just bumping and transferring heat. All right, so one of our concerns is the rate at which energy is transported. Okay. So this is the heat transferred per second. Okay, that's power. Energy per second is power. Okay, this is the thermal conductivity of the material. This is the area across which heat is flowing. Okay, and this is, again, heat flows from a higher temperature to a lower temperature. This is the temperature difference, and that's the distance between the temperature. Okay. So this is what is called the temperature gradient. When the temperature gradient is zero, heat transfer rate is zero. Okay. All right. Higher the temperature gradient, greater the rate of heat loss. Okay, why do we care about this? Okay, so in the summer, we have to keep this room cool, and what you have is heat flowing in from the outside to inside. Okay, and the more heat flows in, the more it costs you to keep it cool. That's money. In the winter, heat is flowing from here to the outside. That's money. Okay, you want to minimize this to minimize the electricity bill. Okay. All right, so of course, this room doesn't have windows, so this is the thermal conductivity for the walls can be made low. But if you want nice, pretty windows, then the thermal conductivity is high, and it's money flowing out the windows. Okay, so that's why you have double and triple pane windows. Okay, so this is the power is the thermal conductivity times the area across which heat is flowing times the temperature gradient. What is this minus sign doing there in that formula? Yep.
Would be like heat transfer, like of heat, maybe? Like, maybe to do with, like with the transfer of heat.
All right, so here, see what is happening here? The temperature is decreasing along this
Is
direction.
it representing an opposing force?
Yeah, so this is dt by dx is negative. So that's what.
Isn't that just a different variation of the Hooke's law of the spring?
No. So, okay. So the temperature gradient is the force that's driving heat flow. Okay. Anyway, so dt by dx is negative, so negative times negative gives you a positive flow. All right, so you have to worry about this kind of stuff quite a bit. Okay. Again, your laptop is using 100 joules, is producing 100 joules of heat per second. Okay. So keeping that laptop cool is not a big deal. All you do is you put a piece of metal on on the CPU. That absorbs the heat. You put fins and put a little fan on it, and that'll dissipate the heat. In server farms, you can have 10,000 of those CPUs. Okay, so you imagine 10,000 computers in a building the size of Walmart. That's a server farm. Yeah. The power consumption is 1 megawatt. That's the heat used by, that's the power consumed by 1,000 homes. Pack 1,000 homes into a Walmart. Yeah. So getting the heat out is a major problem, sir. That air conditioning had better not go down. What would happen?
Everything's not working.
Yeah, everything will drop over and your bank balance will go to zero. Okay. All right, so here's convective heat transfer. Convective heat transfer is heat transferred via warm fluid that is moving, okay? So for instance, here's a space heater. The space heater will warm the air around it, which expands and get less dense than the surrounding cold air. It will rise up, and then that gets replaced by cold air, and eventually all the air in the room gets warmed up. Okay? So a lot of the warm air is right there near the ceiling. Okay? So you should walk around there to have the best conditions. Okay? So I'll show you the Gulf Stream, which transports warm waters across the ocean. So here's the Gulf Stream. Here's a better picture. See, the Gulf Stream goes to the Florida Straits and goes there, and it transports warm, nutrient-rich water all over the oceans. Okay. And that's good for marine life. Okay. This is the amount of water transported is enormous. Okay. So, by the way this Gulf Stream was discovered was Mr. Ponce de Leon 500 years ago was sailing in this direction. And he had good winds behind him and he was going nowhere. And then that's when he realized that there was a sort of a river flowing in that direction. Okay. The current velocity was about 5 miles an hour. Okay. So the Gulf Stream is typically about 100 kilometers wide and 1 kilometer deep. 1 kilometer is, you guys have seen those little planes flying along the beach. So that's about 1 kilometer. Yeah. So the current velocity is fastest near the surface. Yeah. Anyway, so here the Gulf Stream transports 30 million cubic meters per second through the Florida Straits. $30 million cubic kilometers is cubic meters per second is imagine a cube from here to Krispy Kreme on Nova. Imagine a cube that size. That's how much water is transported. Okay, so this amount of water, okay, in the Atlantic Ocean, what are the major rivers that empty in the Atlantic Ocean? What are the two major rivers that empty in the Atlantic Ocean? The Mississippi and the Amazon. And those two rivers only empty, or deposit 0.6 cubic million meters per second. So the amount of water flowing here is 50 times greater. Here it gets to 150 million cubic meters per second. Okay, so again, these currents are extremely important. And with climate change, if these currents get disrupted, we'll have problems. Yeah. Again, you see, there is the most warm air in your attic. Yeah. Now, problem with convective heat transfer is we can't give you a formula for it. Okay? But you do feel it if it's a cold day and if it's not windy, you're fine. But soon as the wind starts blowing, even 5 to 10 miles an hour, you feel quite uncomfortable. That's because convective heat losses have increased. Okay? So what can you do against that? What's the best strategy? Do you want a 1-inch thick sweater or 2 half-inch thick sweaters?
2 100% sweaters
Yeah. Why?
because of air pockets.
Because of air pocket. And that's the idea of a double paned window. That's the idea of a triple paned window. That's why penguins have tiny tufts of hair close to their skin, which are trapping air pockets. All right. So all biology knows good physics, okay? Anyway, okay, so now we'll talk about radiative heat transfer. Okay, heat transfer via radiation. What emits electromagnetic radiation? I'm sorry? Everything. Okay? And here's how much, this is the power radiated. Power is the energy emitted in electromagnetic radiation per second. This is the emissivity of the object. It's a property of the surface. This is a universal constant. That's the surface area of the object. And that's the temperature to the power 4. You double the temperature of an object, and the radiation loss will increase by a factor of 16, 2 to the power 4. Okay, babies have a large surface area to their volume. Okay, so the radiative loss can be quite high. Yeah. So in this room, if you sat naked, you're producing 100 joules of heat per second, you'd lose 50 joules via radiation. Okay? So wearing clothing minimizes that radiative loss. Yeah. All right, so what is the net loss via radiation? Okay, so what is your body temperature? What's your body temperature? 30. Yep. Yep. 37 degrees Celsius, 310 degree Kelvin. Okay. The temperature of the walls is 20 degrees Celsius, 295 degree Kelvin. Okay. So if the temperature of the walls were also 37 degrees Celsius, you would not lose any heat radiatively. Okay. But then you would also be uncomfortable and you wouldn't like it. So what this shows you is the net radiative heat loss. Okay, that's your emissivity, that's the Stefan Boltzmann's constant, that's your body surface area, that's your temperature to the power 4, and this is the surrounding temperature to the power 4. Okay. So again, so this shows you that you are, well, it's sort of showing you you're losing heat. The electromagnetic radiation that you're emitting is mostly infrared light. Okay. And so here's a picture taken using a camera that is sensitive to visible light. Okay, and you can't see your arm. But you take the same picture using a camera that's sensitive to infrared light, and now you can see that, your arms. Okay, infrared light will pass through that plastic cover. Now it turns out that good absorbers are also good emitters of radiation. Okay, so so here's an object. If you shine light on it, if it absorbs most of the radiation, that means it has energy levels that can absorb all the radiation. And those, when you heat those objects, they will also emit all kinds of radiation. Okay. If an object is a good reflector, that means it doesn't have the energy levels to absorb all those radiation. And so when you heat that object, it won't emit all radiation. Okay. So it turns out that dark clothing are good absorbers. Okay, so in the winter, you want to wear dark clothing so you can absorb radiation and be warm. Okay, and in the summer you want to wear light colored clothing. Okay. All right, that covers most of the topics. I'll just tell you a couple of things, interesting things, and then we'll solve problems. I'm going to finish this chapter today. Whatever problems I do is what I'll do. Okay. We'll talk about this radiation a second. Okay, the universe formed 13.8 billion years ago in a Big Bang. And, okay, so there were all kinds of, there was radiation and matter. And so let's say this is 200,000 years after the Big Bang. You had protons and electrons. Okay, so when the universe was young, the average energy of all these particles was the same. Okay. Atoms, hydrogen atoms couldn't form. Why couldn't hydrogen atoms form?
Too hot?
What's that?
Too hot?
What was too hot?
Everything?
The energy of these photons was high enough to ionize this atom that was formed. Do you guys know the ionization energy of hydrogen? Okay, so you're going to remember this forever, for the rest of your lives. 13.6 electron volts. Okay, it takes 13.6 electron volts to kick this electron out from a hydrogen atom. Yeah.
How much was the average photon?
I'm sorry?
How much was the average photon?
Higher than this. Okay. So these atoms could not form. Okay. So, and the universe is expanding. As it's expanding, it's cooling, and the energy of these photons is decreasing. Okay. When the universe became $380,000 years old, the energy of these photons had decreased where hydrogen atoms could form. Okay? So now these guys are not being scattered, and these photons, the universe has become transparent to these photons. Okay, you shine this light, it's not being absorbed by anything, so it will go straight through. And the universe has been expanding, and these photons have been cooling down. Okay. And they have cooled down to a temperature of 2.73 degree Kelvin. And that's called the cosmic microwave background radiation. And that's what these guys discovered in 1965. Okay. These two guys were at Princeton. They were doing some kind of radio astronomy, and they got static noise, and they pointed their antenna in all directions, and the noise was the same. Okay. And so this is the cosmic microwave background radiation. So if you're here, and this is a sphere, all this radiation is coming to you from there. Okay, that's all reaching it. This light took 13.8 billion years to reach it. And you measure the temperature of this, and the temperature of this is everywhere is 2.7 degree Kelvin, okay? Or 2.73 degree Kelvin. Now, one of the mysteries is the following. Okay, let's say this end of the table, if this end of the table is hot and that end is cold, what would happen?
Try to reach equilibrium.
Yeah, heat would flow from here to there, and the temperature would be the same. But what if there is not enough time for this heat to reach from here to there?
You'll have scattered points of heat.
I'm sorry?
You'll have different areas where they're hot.
Yeah, so here's one of the mysteries that happen. All these points are too far away where the temperature couldn't have equalized in 13.7 billion years. Okay? And so that was one of the mysteries of life. And so what happened was in the very first beginning parts of when the Big Bang happened, the universe expanded faster than the speed of light, and temperature became uniform. Anyway, all right, so that's the cosmic microwave background radiation. And what this is showing you is cooler spots and hotter spots. As we said, this is where the galaxies form, the cooler spots. And that was important to find. Okay, so that was, again, that picture won a Nobel Prize. Okay. And you see, it's, so the cosmic microwave background radiation is 2.725 Kelvin. 2.725 Kelvin. And these hot spots and cold spots are 200 microkelvin. So that's 0.2 times 10 to the 3. So this is plus or minus 0.002 Kelvin. So that's what this thing is. So the average temperature is that plus or minus 2 Kelvin. Plus or minus 0.002 Kelvin. All right, one other thing I'll talk about briefly is the following. So again, the average temperature of the Earth was 14 degrees Celsius in around 1800 or 1750. Today it's 15.5 degrees Celsius. Okay, so back then, the amount of heat reaching the Earth was equal to the amount of heat being radiated. Okay, so as long as the amount of heat reaching the Earth is equal to what's being radiated, your temperature will be constant. So for thousands of years, the temperature was constant. And what has been happening is, since the Industrial Revolution, we've been changing the properties of the atmosphere. We've been changing the atmosphere. We've been dumping carbon dioxide. And what that does is, if you dump greenhouse gases, this radiation, this which is infrared radiation, there's less of it being radiated out. So if you're radiating less than what's coming in, then you warm up the Earth. And so that's what's happened. Okay. So what is being radiated is infrared, what's coming in is visible light. And the amount of heat that's being trapped currently is, energy is being trapped on the Earth at the rate of 1600 times 10 to the 12 watts. Okay. Because of greenhouse gases, there's an imbalance of 3 watts per meter square. So for every meter square, this is a meter square. This is a meter square. For every meter square on Earth, 3 watts less is being radiated than is coming in. And what that amounts to is the following. This is equivalent to exploding 20 atom bombs every second and trapping the heat. So that's warming the Earth. All right, guys.